people? This is Roger Skelton. This is a presentation I'm doing on the Leucine zipper. First, before I get to the prompts, I want to break down a little bit what the Leucine zipper does and where it comes from. That helps me wrap my head around it a little bit better. It was discovered in 1988 by a biochemist scientist named Schultz. So don't feel bad if you don't get some of this stuff like me, because it's only about 40-50 years old and a lot of it's still theoretical. So the Leucine zipper participates in quite a few processes for cells in eukaryotes and prokaryotes, but mainly eukaryotes. The most important processes that the Leucine zipper does are cell differentiation and development, regulating gene expression, and transcription factor regulation. Leucine zippers also play a role in programmed cell death. Sometimes, if genetic mutations occur during any of these processes, it can actually lead to cancer. One quick example, because it was kind of hard to find specifics, like what cells are we talking about? Like, is this in every cell? It basically is in every cell. So, for example, your skin cells, let's say you get a sunburn from UV radiation, the Leucine zippers bind to the DNA and help repair that damage from the UV rays. Alright, so on to what actually holds the Leucine zippers together. Let me get out of the way here so you guys can see this. So the Leucine zipper is behind me. This is the best thing I could find on the internet. It's this structure right here. You have two alpha helices. You can kind of see them, they're apart here, but then they come together. And this is the zipper portion where the leucine is binding. So what specifically holds that together is disulfide bonds, ionic bonds, hydrogen bonding, and hydrophobic interaction. The leucine in here is hydrophobic, and the outside of the helices is hydrophilic. So that kind of holds it together a little bit. Oh, let's see. Onto what you could replace leucine with. Basically, leucine is hydrophobic, which that's kind of synonymous with nonpolar, at least in amino acids. So you're looking for a nonpolar amino acid that's also hydrophobic, that's also similar in structure. You don't want it to be too big, otherwise this stuff doesn't work, which you'll see later. So the one I chose was, oh my gosh, I can't read, valine. So valine's also nonpolar, it's also hydrophobic, and it's very similar in structure to leucine. I actually have a thing, let's see if I can get it. This one. Yeah. Alright. Edit this stuff out. So you can see valine is really similar to leucine. You got the typical carboxyl group, the nitrate group, and then, I mean, even these are almost the same. They're basically, your middle CH3 is just flipped. So these are almost identical, so they should work almost the same way and have all the same reactions. It would probably even make the same zipper, if I had to guess. So that's that part of it. Onto which possible residue will destabilize the core. Like we were saying earlier, pretty much if you stick, let me get back to the other thing. Alright, pretty much if you stick any big amino acid in here, it's gonna destroy all that, or make it to where it can't zip up. So something you could put there that would destabilize the core would be tryptophan. Let me pull that up if I can. This visual stuff just helps me a lot, so hopefully it helps you guys too a little bit. So that's this tryptophan right here. I mean, you can see how big of a molecule that is. It's obviously not going to work very well. The main thing that would destabilize the core is this aromatic part right here with the carbon rings. Obviously that's just not going to zip up to alpha helices very good. On to the last thing. And then a different amino acid pair that we could use that interact similar as our pairs involved in this. Let me pull that up too, because it's kind of hard to talk about a lot of this stuff without really looking at it. So this is what this is talking about. It's talking about what pair can we replace here that would have the same electrostatic interactions. So you want to replace lysine with something, you want to replace glutamate with something. I mean, pretty much anytime you're looking for something to replace glutamate with, just say aspartate. It's always going to be aspartate almost all the time. They're practically the same thing. I'll pull that up too. So you can see, aspartic acid, glutamic acid, that's glutamate and aspartate. And you can see how similar they are. So they're going to have the same electrostatic interactions. Last replacement is you would replace lysine with arginine, which you can see behind me again. You have L-arginine here and L-lysine here. So these are all the same on every amino acid, like we already know. And then they have a very similar carbon chain. So glutamate with aspartate, I think. Let me double check that one more time. Yeah, so you would replace lysine with arginine and glutamate with aspartate. And those would have the same electrostatic interactions, or they should anyways. And that's all. Thank you.